All right, let's just continue with the constraints. I've got too little space here, so I'm going to shift this to this one. Now, if you look at the table we put down in the previous lectures, actually it tells you what the constraints should be. There's a constraint on the man hours available in the assembly department. It simply says that whatever time you spend in the assembly department for the production of each type of car, it should not exceed your 30,000 man-hour limit. For the second one, painting and finishing department, the available man-hours happens to be 13,000, and for the last one, it's 6,000. So, assembly department, painting and finishing department, and checking out and testing department. Now, of course, on the left, you write down the actual hours you would spend in each of these departments. If you look back into your table, a Volkswagen uses 150 man-hours for assembly. So that means when you produce X1 units of your Volkswagens, that's the total time you would spend in the assembly department for Volkswagens. For the Volkswagens, you spend 60 man-hours per Volkswagen. So 60 times X2 would give you the total. So 150 X1 plus 60 X2 should be less than or equal to 30,000. That's a linear relationship. Again, constant times variable plus constant times variable. So this is linear on the left. And you require that linear function not to exceed a particular constant, which is 30,000 in this case. For the second one, the constraint will simply look like 50 x1 plus 40 x2, which comes from the second column of your table. And for the last one, it will be 10x1 plus 20x2 less or equal 6,000. Okay? There's one more set of constraints here. x1 is supposed to be greater or equal 0 because you cannot produce something negative. Number 2, x2 must also be greater or equal 0. And typically, we refer to these constraints as functional constraints, and to these constraints as non-negativity constraints. Now, the terminology about these things is not uniform throughout the world. Some people, when they talk about constraints, they mean only the functional constraints. And they refer to the non-negativity constraints as non-negativity restrictions, which is a good term, I think. So maybe I should write it down here, okay? They are kind of special, more special than the functional constraints. So I may be using the term non-negativity restrictions, and if I'm saying just constraints, typically I should be meaning all of them. But sometimes, of course, in the back of my head, I'm going to have the functional ones in mind. If you happen to be confused by this, you just raise your hand and you just ask me which one I mean, okay? Typically, I try to be careful and I try to use functional constraints if I really want to make sure that that's what I have in mind, okay? All right. And the formulation of the problem, I'm going to write it separately here. formulation of this particular problem as a linear programming problem. LP stands for linear programming. Typically, the way we write this down is, I'm just going to repeat what we had before. The objective function is maximization of 2x1 plus x2. Then we write down subject to, which is typically abbreviated to S dot T dot. And the subject to portion tells you what the constraints ought to be. So we simply repeat that. 100x1 plus 60x2 less than or equal 30,000, and 50x1 plus 40x2 is less than or equal to 13,000. And finally, 10x1 plus 20x2 is less than or equal to 6,000 and non-negativity. So I've got 5 constraints here. Okay? Let's call them number 1, number 2, number 3, number 4, and number 5. The linear programming problem, as specialized to this particular example, is the following. Find an assignment of numerical values to the decision variables x1 and x2 such that all constraints 1 through 5 are satisfied, and the objective function is maximized. Of course, if you have a linear minimization problem, then in that case, you replace the term maximized by the term minimized. Okay? All right. So this is the linear programming problem here. And there are 2 parts here. Number 1, you want to assign numerical values to your variables x1 and x2. Number 1, to satisfy the constraints, so that's one requirement. Number 2, of all those such assignments which satisfy the constraints, you want to pick a combination of x1 and x2 that maximizes the objective function. Okay? So that's the second part. That's the optimality part. So we distinguish these 2 parts by the terms feasible solution and optimal solution. It is important to have a good sense of what these terms stand for. Most of mathematics is language development, so you have to be somewhat patient to acquire all this terminology. Okay, that's important. All right, feasible solution. Again, as specialized to this particular problem, a choice of numerical values for x1 and x2 that satisfies all constraints. That's what a feasible solution is all about. For example, if I assign the values 0, 0 to x1 and x2, Is this a feasible solution or not? It's easy to check. You just plug in 0 for x1 and 0 for x2 into the left side of your constraints, which are listed here, and see if your inequalities are all satisfied. And of course, they are satisfied because the left sides are never greater than the positive numbers on the right side. And what is the objective value for this particular solution? 2x1 plus 1x2, which is 0. Okay? So it is feasible, all right, but that simply means don't do anything. Don't produce anything. Fine, then you profit nothing, which is fine for some people, but business people are more eager to make profit than just doing nothing. All right, what about, for example, if I assign the value, say 100 to the first one, 0 to the second. Is this feasible? I don't know. You put down the numbers to the left side and see if they are or not. The first constraint will tell you 150 times 100. That's going to be 15,000. And that's surely less than or equal to 30,000. So the first constraint is OK. The second constraint will tell you you've got, is that, no, 5,000, sorry. 15,000? 150 times 100, that's 15,000, yeah. What about the second one? That'll be 5,000, right? 5,000 less than or equal to 13,000. That's also satisfied. And the last one is 10. So it will be 1K less or equal 6K. So all of them are satisfied. So this is also feasible. Okay? The profit value is how much? 200. All right. This looks elementary, but for some people, these things don't really sink in. That's the reason I'm giving all these numerical examples, because I do not want you to miss anything. If you already are familiar with all this stuff, fine, you just have to be patient, okay? This is for people who are newcomer to the situation. All right. What's an optimal solution in that case? An optimal solution is just a feasible solution such that the objective value obtained or induced by this solution is either equal or greater than the objective value induced by any other feasible solution. So by the solution is equal to or greater than the objective value of any other feasible solution. Again, you want to make these things operational. So let me put down extra stuff here. A solution with x1 assuming the particular value, say x1 bar, and x2 assuming the value x2 bar, is an optimal solution if this solution is feasible and additionally the value you get for x1 bar plus x2 bar is greater or equal the value you would get for x1 plus x2 for every feasible solution x1, x2. Okay? You have to be precise about these things. Why do I keep repeating this? Because I've seen so many students who thought they actually mastered the idea, but then all of a sudden in the exam you find out that they have not. Okay? Maybe it's not one of you, but nevertheless, you know, I taught this sort of stuff for 30 years, and I know by experience that this happens. Okay? It's been that long, huh? 30 years. Long time. Okay. So, let's talk about the solution concepts now. Now, again, many of you are familiar already with what I'm going to do right now. Nevertheless, for those of you who may not be familiar, I'm going to give you the so-called geometrical or graphical solution way of attacking the particular problem we have on hand. The problem we have on hand involves only two variables. That's why we can attack it using a graphical way. How do we do that? Well, we simply assign one axis to the x1 variable, assign the second axis to the x2 variable, and that gives you a planar region in the x1, x2 plane. Any point on that plane is just a possible solution, which may be feasible or not. Nevertheless, it's a proposed solution. So, when you have two variables, say x1, x2, we can represent everything in the x1, x2 plane, defined by two axes. So that's what I'm going to do. x1 axis, x2 axis. Now again, when you pick a point here, such a point has got two coordinates. One coordinate is here. So if this point is, say, x bar with x1 bar, x2 bar, I put a bar just to make sure that it's a particular solution, whereas x1, x2 is generic. It can stand for anything. Okay? All right, so this is a particular solution where the x1 bar value is just whatever number you've got here, and x2 bar is whatever you've got in the vertical axis. Okay? Looks trivial, but people sometimes they miss it for some reason. I don't know. Of course, you cannot really imagine what everybody has in his or her mind. Nevertheless, this is really straightforward. Okay, so let's go now to the representation of the feasible region. The feasible set of solutions in the x1, x2 plane. I'm going to take my constraints in equality form. So 150x1 plus 60x2 is equal to 30,000. That's the equality version of the first constraint. Okay? The second one is simply 50x1 plus 40x2 equal to 13,000. And the last one is 10x1 plus 20x2 is equal to 6,000. These are the defining equations for your constraints. Coin the term, write down the term. Defining equations for your functional constraints. Well, let's include also the non-negativity restrictions. The defining equation for the first non-negativity restriction is x1 equal to 0. For the second one, it's x2 equal to 0. So, defining equations for your constraints. Okay? Why am I interested in the equations rather than the inequalities? There's, of course, one reason. These are linear equations, so you can just draw straight lines to represent them. Number two, when you talk about a feasible solution, you ask for a combination of x1 and x2, which satisfies each constraint either as an equation or possibly as a strict inequality of the less than kind. Okay? So, of course, the less than kind type of inequalities can be derived from the equations once we have the picture for the equations. All right, so the first equation is just a linear line. It's a line. It's got intercepts at x1 equal to 0 and x2 equal to 0. When you put x1 equal to 0, you solve for x2 and you get, what do you get? 500? 500. That's one intercept. For the second one, x2 0 means x1 is 200. Yes. I'm not very good with numeric computation, so if I make a mistake, you correct it, okay? And for the second one, we've got 0 for x1, which means x2 is, what is that? 325? 325. And when x2 is 0, x1 will be how much? 260. Thank you. It was a hard computation. All right. And the third one has, what is it? x1 0 means x2 is 300, right? And when x2 is 0, x1 is 600. So these are for constraints number 1, number 2, number 3. For number 4 and number 5, when one of them is 0, the other one, it's concealed here. The other one is simply 0 times x2, actually. Okay? So whatever you assign to x2, it doesn't really matter. For that reason, both of these lines go through the origin. So there's only one intercept, which is not an intercept, it's just the origin. Okay? They go through the origin. Okay, so when I look at my x1, x2 plane, I'm going to plot these intercepts. So we've got 1, 2, 3, 4, 5, and maybe 6. Yeah, whatever. I think it goes up to 5. Yeah. And the other one has 1, 2, 3, 4, 5, 6. The largest one is 600. This is the x1 plane, x1 axis. All right, so the first intercept is 0, 500, which is this one, and 200 and 0, which is that one. So that's my constraint for number 1. Well, the equation version, okay? The next one is 0, 325. So 325 is somewhere here. And 260 is somewhere here. So it goes something like this. That's your number 2. Number 3, 0, 300, which is that point, and 600, 0, which is that point. So I've got that one. That's my number 3. Number 4 is x1 equal to 0. Well, x1 is equal to 0 along the vertical axis. Each point along the vertical axis has a coordinate of 0 for the x1 component. Okay? So this is number 4. And number 5 is the horizontal axis, because every point on the horizontal axis has a x2 value of 0. Okay? All right. So I've got my lines. Now my actual constraints are less than or equal to or possibly greater or equal form. First of all, let's handle the number 4 and number 5. Number 4 says x1 is either 0 or greater than 0, which means that which one is that? x1, x1 is this way, yeah. So number 4 says you want to go along the horizontal axis from 0 up to plus infinity. Okay? That's what it says. Number 5 says x2 should be greater or equal 0. You are equal to 0 on the axis, and you are greater than 0 here. So, since I have to satisfy both number 4 and number 5, I'm in the first quadrant of the plane. Okay? But then we've got also the other ones. If you look at number 1, you are either on top of the line, or you are either on that side or on this side. Just check for one point, for example, the origin. The origin satisfies the inequality. For this reason, you have to be going this way. It's easy to check. Okay? Unless, of course, your line passes through the origin. In that case, you have to check some non-origin point. Okay? All right. Number 2 says, again, similarly, you should be here. Number 3 says you should be this way. So, looks kind of complicated, but your points, your combinations of x1, x2 values must satisfy all constraints at the same time. So, this region here consists of all points x1, x2 that satisfy all the constraints. That's the feasible set. Now, the question is, I've got infinitely many, uncountably many points in the feasible region. So if I want to pick a feasible point which maximizes my objective function, I should somehow be able to do it, if I can. Of course, you already know how to do that from your elementary linear programming type of courses. At least some of you know that. But we'll just go through that here as well. So let's focus now on the optimal set of solutions. In general, you may have more than one optimum solution So if you've got alternative solutions, you want to identify that as a set. Okay? Each one does the job. You may also have a single optimal solution, in which case, of course, it's better to talk about the optimal solution rather than an optimal solution. Okay. In this case, we don't know which one will be the case. But let me just reproduce the graph we had. It looks something like this. Where the first one, this is number 3. This line is number 2. The next line is number 1. And we've got number 4 here and number 5 for the bottom line. Okay? That's my feasible region with these corner points. So we're investigating the objective function now, which is defined by z equals to x1 plus x2. What you do is you pick a value for z, make it a constant, and then a constant equals to x1 plus x2 gives you an equation. So you can draw it, and then you pick another z, you pick another value for z, that gives you another line. And so, for example, if you pick z equals 0, the equation you get happens to be this one. It passes through the origin because x1, 0, x2, 0 means you satisfy the equation. All right, so I know that 0, or the origin, has an objective value of 0. And it turns out that the slope of this will be defined by the ratio of 2 to 1, which is a little vector here going 2 units this way, 1 unit here, up, okay? And so this is the vector 2, 1. I don't know if that's visible from the camera, but nevertheless, it's what it is. All right, turns out that if you look at all possible combinations of x1 and x2 as a line, it will be perpendicular to this vector 2, 1. So it will look something like this. I hope I can draw this correctly, because I want it eventually to go to the correct point. You know, my drawing may not be too correct. Nevertheless, we'll see if that really captures the information. All right, what about z equals, say, 1,000? Well, I don't know, maybe I don't. That's too large. Let's make it 100, okay? In that case, of course, the equation will be 100 equals to x1 plus x2. What are the intercepts for this? Well, 0 and 0 for the first and second components. When the first component is 0, x2 will be 100. When x2 is 0, x1 will be 50. So it goes through the points 0, 100 and 50, 0, which is somewhere like this. Okay, so the first one had z equals 0. The second one has z equals 100. And you can see that as I increase z to larger values, perhaps make it 200, in that case, of course, the intercepts will shift to twice as much. So you can see that these things will be all parallel. And the larger the value of z, the further upwards and to the right this line moves, always keeping itself parallel to the original line or keeping itself perpendicular to the little vector 2, 1 at the origin. Okay? And when you do this, it keeps going, and eventually there's a point of exit where if you move the line further to the right and upwards, you will have no connection to your feasible region. It will not give you any feasible point. Whereas up to that point, I don't know what that point is. So let's just call it z bar. I don't know what it is. Nevertheless, there is such a z bar just from the graph. Okay? So any number you assign to z between 0 and z bar will give you a line passing through the feasible region, which means that if you pick, for example, look at this line. For z equals 200, if you pick any point along the solid portion of the line, all these points, each point on the solid portion of that line is a feasible combination. So each one gives you the same objective value, 200. They are not better than one another. They are equally good. But they are all better than the lines or the feasible set of solutions you would get here, because each one here will give you 100. Okay? So you can see that at this point, this particular line has exactly one feasible solution in this case, which is feasible and which gives you the best value, because any further increase in the value of z from z bar upwards will take you or will make you infeasible. Okay? So that's the idea here. So we need to compute this point as well as the value z bar. That will be the best combination. So this is my optimal solution, the optimal solution in this case. How do I compute it? Well, it's really straightforward. This point happens to be at the intersection of lines 1 and 2. So you just write those equations down and solve for your x1 and x2. What's the equation for number 1? 150 x1. So this is the way you compute. 150 x1 plus 60 x2 equals z bar. The second equation, sorry, it's not z bar. It's 30,000. And the second equation, 50x1 plus 40x2 equals 13,000. So what you do is you multiply the second one by -3 and add it to the first one, and you get 0 here. And you get 120, so that will be -60. x2. And how much is this? 39 minus 30 minus 9,000. So this gives you x2 equals 9,000 divided by 60. How much is that? 450? 150. Thank you. You guys are better at computations than I am. Okay. x2 is 150. And how much is x1? Well, you use either the first or the second equation 60 times 100, well, how much is it?
140.
140. You can solve for that using, for example, the first equation. Okay? Then, how much is z? 2 times 140 plus 1 time 150. That's 280 plus 380, 430. So, let's put our bars here because these are particular values and that's the optimal solution. Okay? So my optimal solution is 140, 150 with an objective value of 430. Okay? That's it. That's your solution. That's your optimal solution for this example. Of course, this graph can be used only for 2 variables. Or you can, if you are somewhat patient and can draw things in 3 dimensions, you can also do it for 3 variables, x1, x2, x3. After that, God help you because you can't do it, okay? In your head, you may see it perhaps. Some people have a way of visualizing things. So for that reason, this is very limited. So don't be tempted to use it all the time. Nevertheless, it gives you good insights about what's happening with these kinds of problems. After that, after the 3rd dimension, you have to rely on algebraic methods. That's why you need the simplex method, okay? Because typically, the linear programming problems we deal with may involve thousands, sometimes millions of variables. You've got too many, okay? All right. Any questions on any of this stuff? All is mastered. Good. So this example tells you what the basic structure is. Now let's talk about the general form of the linear programming problem, which essentially represents any linear programming problem that you may encounter using numerical values. So I'm going to use the constant n, which is generic here. It can stand for any positive integer, for the number of variables of the problem. And I'm going to use m for the number of functional constraints of the problem. And I'm going to go for the easy case first, the canonical form maximization, which is a particular type of linear programming structure, because it agrees with the example we had just before. Some people, instead of using the term canonical, they may refer to the kind of problem I'm going to write down as a standard form problem. So you might want to make a note of that. So again, the terminology is not uniform for these things. Okay? Different people prefer different terms. Nevertheless, the canonical form maximization I have in mind will be the following kind. My variables will be x1, x2, up to xn. So I've got n variables. These are my decision variables, or just variables. Now I'm going to have certain constants, C1, C2, Cn, associated with the variables x1, x2, xn. These are the objective function coefficients of the variables x1 up to xn. Okay? Then I've got numbers A11, A12, A1n. These are numbers. These are the left-hand side coefficients for constraint number 1. Okay? The first functional constraint. And then, of course, you've got such numbers for each constraint. The ith one will have AI1, AI2, so on and so forth, AIN. These are the left-hand side coefficients for the ith constraint. And finally, we've got the mth one, AM1, AM2, AMN. The left-hand side coefficients for the last one. Okay? So, you have an array of numbers for each constraint. Each array has n coefficients. Some of these coefficients may be missing, meaning that they are actually 0. They are not missing at all, they are 0. Okay? What else do we have? The right-hand sides. I've got B1 up to Bm. These are the right-hand side constants for your constraints. As I said, when I refer to constraints, I mean the functional constraints. Okay? All right, so I've got 3 pieces of information, CJs, AIJs, and BJs, and this is the data of the problem, which means that somebody tells you what those numbers are. If someone tells you what those numbers are, or if you are able to deduce it from this problem situation, you have an instance of the problem. Otherwise, you have the generic form, which represents a family of instances. How many members in the family? As many as you cannot count. There are infinitely many, okay? Uncountably many. So, instances are different from the general linear programming structure. This is the structure. We haven't written it down yet, but I'm going to write it down in a minute. So, you want to maximize a linear objective function, which is C1, x1, C2, x2, Cn, xn. That's your objective function. If you want to include the value of the objective function, again, traditionally people use z for that, subject to the conditions, the functional constraints, a11 x1 plus a12 x2, a1n xn less than or equal to b1. A2, well, let's write down the ith one. AI1 x1, AI2 x2, AIN xn less than or equal to bi. Typically, we don't write them all down. We just write the ith one, and then we say I going from 1 to m. Okay? But nevertheless, this is the first exposition, so I write them all down. AM1 plus AM2, AMN xn less or equal bm. These are the functional constraints. And finally, I'm going to assume all variables are non-negative. So these are the non-negativity restrictions. Canonical form refers to, well, canonical form maximization refers to the maximization of a linear function subject to less than or equal to type functional constraints with non-negative variables. There are many types of deviations from these, but nevertheless, we'll go into that later. The short form for this is to minimize Cj xj, j going from 1 to n, subject to summation aij, j going from 1 to n, less than or equal to bi, and this is repeated for each I going from 1 to m. So this is a family of constraints in compact form with xj non-negative for each j. Short meaning, you use less symbols here, but I don't like personally summations and stuff like that. You know, if you're comfortable with that, fine. Personally, I would like in your head to see everything one at a time. Okay? It's better that way. We finish it here. Next time, on Wednesday, we have 1 hour. So we'll just continue with this stuff. Neresi? Ha, şurası. Yes, there's an xj here, sorry. Yeah. Ah, sorry. The last minute mistakes. Yes, this is a maximization because that's what we began with. Sorry about that. Okay. Time constraint makes you make mistakes, huh? Okay.